Thanks very much for joining this online talk, and thanks very much to the organizers for making this conference possible under these circumstances. Today I will talk about a new construction of error-correcting quantum codes. Let's consider previous LDPC quantum codes with large distances. So first of all, there's the Tori code by Kitaev from 1996, which encodes 2 logical qubits and has distance scaling with the square root of the number of physical qubits. Later, Friedman, Meyer and Luo showed that actually a better scaling of the distance is possible using a quite involved topological construction, and they prove that the distance of their code family grows as 4th root of log n times square root of n. Much later, Eva, Kaufmann and Seymour showed that one can improve the Friedman-Meyer-Luo bound using product constructions and so-called Ramanujan complexes. And they prove that their code families has distance scaling with square root of log n times square root of n. And shortly after, Kaufmann and Tesla showed that by taking iterated products, it is actually possible to obtain arbitrary polylog violations of the square root of n scaling. But all of these have this polylog square root of n scaling, and some people believed that actually this is all we can hope for. But then Hastings O'Donnell in September 2020 showed that this bound can be violated by introducing a family of quantum codes whose construction is inspired by fiber bundles. And they show that the distance of their code family scales as n to the 3/5 up to some polylog factors. Shortly after, in December, Panteleev and Kalachev showed that in fact it is possible to increase the distance, sacrificing the number of encoded qubits, using this parameter alpha that you can see. And with their construction, it's actually possible to get as close to linear distance as one wishes. Almost simultaneously, we introduce balance product codes, for which we prove that their distance scales as n to the 3/5. And in contrast to these earlier constructions, which are both random, our construction is explicit, meaning that we do not require any randomness, and there is a deterministic efficient procedure to construct these codes. I've just referred to these new codes as twisted product codes. So in order to understand them, let us first review how we can take products of classical codes to obtain quantum codes. Let us consider the example where we take the product of 2 repetition codes, which we will think of in terms of line graphs, where bits and checks are associated with the vertices and edges of the graph. Taking the Cartesian product gives a 2-dimensional object with vertices, which consist of products of vertices of the input graphs, edges, which are the product of a vertex and an edge, and faces, which are the products of 2 edges. It turns out that this is in fact the surface code, and there is an algebraic description in terms of tensor products. So the surface code is a tensor product of 2 repetition codes. To reiterate, we can take the product of 2 classical codes to obtain a quantum code. So let's stick with this geometric intuition and consider different products. So first of all, what we just saw is a simple Cartesian product. We can take any 2 geometrical spaces, so let's say a circle and an interval, and take the product, and in this particular case we obtain a band. But there are more complicated products possible. So we could take the same input spaces, but we introduce a twist, and this would give us a Möbius strip. And the mathematical tool that allows us to describe these kind of products are fiber bundles, which view these products in terms of a base and a fiber. So for this Möbius strip, we could imagine that the base is simply the circle and the fiber is the interval. So now in this space, moving between open sets is described by a transition function, which kind of tells us how to move between small open sets. What Hastings-Howard did was they extended the notion of tensor product of two classical codes by introducing a similar notion of transition functions and twists into the language of codes. So this allows them to take products of classical codes with twists. And it turns out that these twists enforce, in some sense, detours that the logicals have to take, and this increases their weight. We will see concrete examples of this later in the talk. Earlier, I gave the Möbius strip as an example of a non-trivial fiber bundle, but this does not give rise to an interesting family of quantum codes. What Hastings-Howard did was they considered fiber bundles where a random code is the base and the fibers are simply repetition codes. The twists in the fibers are also chosen at random. They prove that if we choose a random code as a base and we choose our random twists, then with high probability we obtain a quantum code with distance scaling as n to the 3/5 up to polylogs. And our starting point was to see whether we can do this explicitly, meaning without introducing any randomness. To this end, we introduce balanced product quantum codes. Just as the usual tensor product, it takes two classical codes as an input, but in addition to this, we assume that there's a symmetry group acting on both of these codes. The balanced product is then essentially the tensor product, but in addition to this, there's a symmetry reduction, which reduces the number of physical qubits while leaving the distance more or less invariant. Therefore, we obtain a quantum code which has better properties than the simple tensor product. But for this to work, we first need to obtain classical codes with a large number of symmetries. So how do we get these codes? In order to construct classical codes, which have large symmetry groups, we need expander graphs. These are graphs which are very strongly connected. Below you can see an example where we indicate some subset of vertices S in red and edges which connect vertices in S with vertices which are not in S in blue. We call the set del S. The Chia constant, which measures the connectivity, is defined as the minimum quotient of del S over S. So, for example, the complete graph is very well connected, whereas this other graph is not very well connected. This is because we can simply take as subset S all vertices of the left-hand side, and then del S is only the single edge. Note that the Chia constant also kind of tells us about how easy it is to disconnect a large portion of the graph by cutting only a few edges. We are interested in expanders with a constant vertex degree, so the complete graph is a kind of a trivial example, and these are non-trivial to construct. We know that graphs which embed nicely into Euclidean space of any dimension can't be good expanders. Let's look, for example, at 2D or 3D Euclidean space. In 2D, if you look at some circular neighborhood, then its area will grow quadratically with its radius, whereas the boundary only grows linearly in the radius. Similarly, in 3D, the volume of a neighborhood grows cubically with the radius, whereas the boundary grows quadratically with the radius. So this means that if you want to disconnect some neighborhood S in Euclidean space, then the ratio of del S over S grows as r to the dimension minus 1 divided by r to the dimension. And taking r to infinity, this quotient vanishes. However, this is not true in hyperbolic space. So here you see an example of 2D hyperbolic space with some graph embedded into it. And you can see that if we take some subset S, then the number of edges sticking out of S grows with the size of S itself. It turns out that when we look at families of graphs, there are limits to the asymptotic expansion of this family. And this is the theorem due to Allon and Breuckmann. There exist graphs which have optimal expansion, so which fulfill this Allon-Breuckmann bound, and these are called Ramanujan graphs. There is an explicit construction of this family of graphs due to Lubotsky, Phillips, and Zarnak. And this is based on Cayley graphs of PGL2 over the finite field or PSL2 over a finite field. Sips and Spielman in 1996 showed how we can construct interesting families of codes by combining families of expander graphs with local block codes. In particular, they show how to obtain families of classical codes where the number of encoded bits scales linearly with the size of the code, and the distance also scales linearly with the size of the code, and they show how to obtain a linear time decoder. So let us consider a concrete example. The graph that we want to consider is a degree 7 graph that is embedded on a compact surface of negative curvature. So this is why we will call it a hyperbolic graph. You can see this surface rotating in the upper right hand corner, and I also have a little 3D model here, as you can see. And in this graph we identify edges with bits and vertices with parity checks, but in a different way that from what you might be familiar in the Tori code. What we want is that the edges around a vertex form a valid code word of a local code. As this is a degree 7 graph, we need a local code of length 7, and we choose the 743 Hamming code. Notice that we actually have to choose a labeling around each vertex, which assigns which edge corresponds to which bit in the local code. But let's take this as a given for now. In the bottom right hand corner, I have written all code words of the 743 Hamming code up to cyclic shifts. So the 743 Hamming code is a cyclic code, so it is invariant under cyclic shifts. Now let us try and construct a code word of the global code. Without loss of generality, let's first try and fulfill a parity check around the center vertex. And we choose just the third code word in this list. So you see there's 0, 0, 0, 1, 0, 1, 1. And this is symbolized in this picture by turning edges thick. Now we see that the center vertex or check is fulfilled, but we have created 3 more problems in its neighborhood. So now let's try and fulfill this leftmost vertex or check. So we choose to put in another code word of the Hamming code. You see that we immediately have created 3 more problems. Now trying to fulfill this lowermost vertex, again we create 3 more problems. And this is just due to the fact that the Hamming code has distance 3. Carrying on like this, we can find a code word of the global code. But notice how this code word has quite large support. And what I wanted to show with this example is how the expansion of the graph plus the distance of the local code will enforce that code words have large weight. The code that we have constructed encodes 12 bits. And here is the basis of the code space. What Sips and Spielman showed was that if the expansion of the graph and the distance of the local code are large enough, then the distance of the resulting code is lower bounded by a constant times the number of bits. This constant will depend on the degree of expansion and the distance of the local code. Further, it's very easy to prove a lower bound on the number of encoded bits k. The constant in this case will depend on the encoding rate of the local code. Using a suitable family of expander graphs, we thus obtain a code family of classical codes such that k and d scale with n, and such codes are called good codes. Let me now try to visualize what a balanced product might look like. So let's say we have this repetition code, just a circle, and let's say we have an order 3 symmetry acting on this repetition code, so we can just rotate it like this. Similarly, we have this piece of paper which symbolizes our code defined on a surface. And let's say there's another symmetry of order 3 acting on this. And I will just draw the orbit of a point mapped under this. So this point gets mapped onto this point, gets mapped onto this point, and then let's say we have periodic boundary conditions, and we end up here. So now the balanced product of this repetition code and this surface code is simply defined by aligning the points, so they lie on top of each other, and then gluing in this repetition code at this point. And this happens all over the surface. So in this example we just saw how we can in some sense glue in a repetition code into a code defined on a surface which has a certain symmetry, exploiting the symmetry acting on both the repetition code and the code defined on the surface. Compare this to the fiber bundle and lifted product codes, which are defined in terms of a base and a fiber. The balanced product codes offer a different point of view, where the horizontal part, given by the code defined on the surface, is simply a single large classical code. Note that this gives us an intuition for where the large distance of these new twisted product codes comes from. One side of the stabilizer checks and some subset of the qubits essentially see nothing but a good classical code. Let us consider another example of a balanced product, this time of two repetition codes, one of distance 3 and one of distance 6. Both are acted on by the symmetry group with 3 elements, Z3. It acts by 120-degree rotations. The outcome is topologically a torus, and in fact the quantum code coming out of this is a toric code. But note that given its distance 3, the number of physical qubits is lower. The usual toric code with distance 3 has 18 physical qubits, but here we only need 12. However, it has the same local structure as the usual toric code. This little model illustrates how the repetition code wraps around the torus. Let's review the formal definition of a balanced product. I will go through this very quickly, just for the experts. Let's say we have two topological spaces, x and y, on which some group H acts on the left and on the right, respectively. Then we first can take the Cartesian product and consider a point in this Cartesian product, given by x in x and y in y. And we define an anti-diagonal action of the symmetry group H on these pairs. Then the balanced product is a topological space, which is simply given by the quotient space, where we quotient out the action of H. The balanced product codes that we consider in our paper are defined from Cayley graphs of PGL using the construction by Lubotsky, Phillips, and Zarnak. As PGL is a well-understood group, we know its order and we understand that it has a suitable cyclic subgroup, H. And we can also show that local codes with good properties exist so that we can define an expander code. Now, given this expander code, with the action of a cyclic group on it, we can take the balanced product with a repetition code on which the cyclic group acts. We obtain a quantum code with the following properties. First of all, the number of qubits is simply 3 times the number of edges in the expander graph. The number of logicals scales as n to the 2/3. The z distance is linear in n, and the x distance is n to the 1/3. The reason for the z distance to be linear in n simply stems from the fact that the x checks are coming from a good classical code, which is just wrapped around itself. The intuition for the x distance is as follows. The z checks are essentially coming from the repetition code that we glued in. This repetition code has distance q, as it's scaling with the size of the cyclic subgroup of H. But q grows with the third root of the total size of the code. Now, taking the product with a suitable classical code again allows us to balance the distances. So the final quantum code that we obtain encodes n to the 4/5 qubits and has distance lower bounded by n to the 3/5. It would be possible for us to attain better bounds in terms of distance if we knew of different Kelly expanders with the correct properties. So let us consider another concrete example. On the top, I've drawn a genus 14 surface on which we can define an expander graph and subsequently an expander code. I have indicated in red an orders 13 cyclic symmetry, which essentially translates through the surface. On the bottom is just a circle which indicates the repetition code. Along the orbit of the symmetry, we identify points in both the surface and the repetition code, or the circle. So we can just go around and we glue in the circle into the surface. Note that this happens throughout the surface, not only on this one path. As a local code, we can choose the Hamming 4743 code, and the quantum code that we obtain has the following parameters. First of all, it has 546 physical qubits, it has 6 logical qubits, and using Monte Carlo techniques, we can bound the x distance to be at most 13, and the z distance to be at most 18. Note that the x distance is expected to be 13, since the repetition code has distance 13. The check weights are weight 6 for x checks and weight 4 to 8 for z checks. Let's compare the balanced product to lifted product codes by Panteleev and Kalachev. In their construction, the base code is structured. However, they consider random lifts in order to obtain fibers with random connections. Their work is cast in the language of commutative algebras, which implies that the fiber always has to be a torus. They gave improved distance bounds over Hastings-O'Donnell that we also make use of in our paper. There is an overlap between balanced product codes and lifted product codes. Note that all codes constructed in the lifted product codes work, in the fiber bundle code work, in our work, all belong to the same subclass. However, there are lifted product codes, which are not balanced product codes. These stem from commutative non-group algebras. However, there are also balanced product codes, which are not lifted product codes. And these stem from non-commutative or non-free group algebras. The latter part is quite important, as it led us to a conjecture of good LDPC quantum codes. The intuition here is, we have seen that having one good classical code on one side leads to a linear distance. So why shouldn't we just take a balanced product of two good expander codes instead? So here's our conjecture. Let's consider two expander codes, and let's take the balanced products between them, factoring out the total symmetry group acting on both of these codes. We conjecture that this is in fact an LDPC quantum code which is good, meaning that it has a linear number of encoded logical qubits and a linear distance. In fact, we can already prove that the number of encoded qubits is linear. So let me summarize. Balanced products are a powerful tool to explicitly construct quantum codes with excellent parameters for classical codes. I have mentioned this in this talk, but in fact we can take balanced products of arbitrary block codes as well. We could use this to construct small examples. It's similar to the other twisted products, meaning lifted products and fiber bundle codes. However, we eliminated the need for randomness, which might be advantageous if we want to build these codes and we would need to schedule the syndrome extraction circuits. And our construction is symmetric in its factors, so this leads to to the conjecture of good quantum codes. So far we do not have any decoders exploiting the full distance. Thank you for your attention.